Hello, and welcome everyone to this afternoon's Turn seminar, where we're talking about climate modelling in Australia with a provocative subtitle, What's the Use? And of course, this talk is all about benefits for human health, society and the environment. And, the first thing I want to do is to acknowledge the traditional owners and custodians throughout Australia and New Zealand and all nations, where we honour their profound connections to the land, water, biodiversity and culture, and pay our respects to the elders past, present and emerging. And today we have many people from all over the world that have joined us. Thank you very much for that. And I welcome particularly Lynn Beazley, who we have named this seminar series in honour of. Hello, Lynn. If you're there, say hello. No, we'll move on. And welcome also to current and past Turn board members who have joined us today. So today's, just a bit of an introduction to Turn. We are Australia's terrestrial ecosystem observatory, and our work is enabled by a lot of good people out there. We have funding from the Australian government through the NCRIS program, from state governments, and also from a whole range of partners in universities and CSIRO. So we're very proud of that. And the main event for today, of course, is a panel of speakers. We're going to hear from Professor Andy Pitman about climate modelling itself. We're going to hear from Dr. Ivan Hannigan, who's going to take the health aspect, and then finally from Professor Lauren Rickards, who's going to tell us something we hadn't actually thought about with research impact. And I'd just like now to introduce you to Professor Andy Pitman, who is a Fellow of the Australian Academy, and he's a member of Turn Science Advisory Committee. Thanks, Andy. He's a passionate science communicator, and his distinguished career related to atmospheric science has had international impact. And Andy is currently the director of the Australian Research Council's Centre of Excellence for Climate Extremes. And I am now going to hand over to Andy to take it away. Thank you, Andy.
Thank you, Beryl. Welcome, everybody. I shall share my screen. And hopefully everybody can see that slide. I shall continue on the basis that everybody can see that slide. So thanks for the invitation to speak. I was asked to really give you a quick rundown on what's going on in climate modelling in Australia. So first of all, for those of you who don't know, the CMIP6 ensemble, which is the coupled model intercomparison project version 6, those results are now available online. So you can get at those data. They're available via the National Computation Infrastructure Facility. And quite critically, those provide projections under various emission scenarios, predictions, and some new very high resolution modeling simulations. So in those of you familiar with earlier projections work, that tended to be just projections associated with higher CO2. But the new phase of CMIP have included predictions, sort of decadal to century scale predictions, and some very nice high resolution simulations. And those provide us with quite phenomenal resources for exploring the impact of climate change over Australia. But there are limits. Global climate models are phenomenal tools for simulating large-scale climate, but most adaptation and indeed most mitigation strategies, at least as they relate to terrestrial processes, operate at scales very, very much smaller than the granularity of global climate models. In addition, global climate models, though they are phenomenal at giving you large-scale information about how climate will change, lack the fidelity to say a great deal about how major extremes might change. And I don't mean here the hottest day of the year, the wettest day of the year. I mean extremes that might occur with a probability of once a decade, once a century. Climate models struggle with that. CMIP6 the new data won't resolve those problems. There are significant concerns over some CMIP6 models. Secondly, my personal view is the world has the capacity to support 20 models, and there's about 100 submitted to CMIP6. And I think it's a reasonable assertion, though I would struggle to defend it, that perhaps 20% of those 100 models are useful. Certainly, they are not all independent, and certainly they do not all share the same level of skill. The good news is the Australian climate model that was developed under the leadership of CSIRO with input from the university sector, the access models work extremely well, and Australia should be very proud of the skill and the fidelity of the models that we have submitted to CMIP6. But taking all that into account, it's a really important thing to understand that climate models are not weather scale resolving. So if you are interested in systems vulnerable to extremes, and many people are for adaptation, then the climate models are almost certainly underestimating how extremes will change, and certainly don't tell you the regional detail of how extremes will change. The fundamental thing to understand is CMIP6 is designed for scientific inquiry. It's designed for basically the same reasons as you build a particle accelerator or you build the Giant Magellan Telescope. It's designed for scientific inquiry. It's not an operational system for decision making. So it's really important that we understand the utility of our global climate models, what they're good for, what they're not good for, where we can use them and where we can't use them. So given those caveats, what do we do in the short and long term? Well, in the short term, and I mean, what do you do in the next 5 years if you are desperate to understand how climate will change relating to a system that you're interested in? I think the first step is to kick out the hopeless models. What I mean by that is you need to do a systematic evaluation on the key attributes of a climate model over a large region, and from that select 20 models that seem to work well. You can't trust other people's evaluations. You can't just go to the literature and find someone who says this model works well or this one doesn't. You need it to work well for your particular purposes. And yeah, I accept that that's a lot of effort, but it leads to an outcome where you're using more reliable models. Secondly, you need to test for the independence of the models, because it's possible that all 20 that you pick have the same characteristics. So you need to make sure the models are independent. And then you need to use each model separately. I get very nervous when people calculate ensemble averages, especially because ensemble averages average out the extremes. Then we're recommending the use of expert judgment, which is a strange thing for a climate scientist to recommend when we have all of these quantitative tools, but bring in local meteorologists, bring in people from the Bureau or from the universities who understand the meteorology in the region and use their expert judgment to help build storylines or scenarios from which you can test your interested systems. And I know this isn't necessarily a popular view, you do need to recognize there is little useful skill in most variables at scales below a large region. I know people downscale climate models to a few kilometers or less, and that's perfectly fine in terms of writing academic papers. But please don't believe the data that you're looking at, because it's not something that you would trust for decision making. You could also downscale for bespoke projects. There is skill in doing that, as long as you do it for the specific project you have in mind. And you remember that downscaling for specific projects solves some of the problems some of the times. Very hard to downscale global models and get a good expression of how extreme events might evolve within the system that interests you. Longer term, well, the thing that interests me are extreme events. And extreme events are an expression of weather scales occurring in a warming climate. So I want you to imagine a global system that's warming, and within that warming, the weather is responding, and the weather is changing in response to the long-term trends. Well, climate models do those long-term trends at the continental or global scale really well, but they don't do the weather. So what we need to do is translate our global climate models to be weather resolving. So we begin to simulate how weather events, for instance, the sorts of heat waves we saw over Canada, which were connected to the heat waves in the Baltic states, which were connected to the extreme rain over Germany, which were connected to the extreme rain over China, how the systems that translate the global trends into weather phenomena can be captured. And the reason we want to do that is that for many systems, it's the extremes that count, whether it's hail, whether it's lightning, whether it's cyclones, whether it's extreme winds, whether it's the combination of droughts and heat waves, or the combination of extreme rain and extreme wind. These are weather scale features, and we're trying to get to the point where we can simulate those in our global models. And the good news is it's actually not just a scientific problem. It is a scientific problem to do that, but it's substantially a computational problem. And the ARC Centre of Excellence for Climate Extremes, led out of research communities based mostly at Melbourne Uni and Monash, in collaboration with Bureau of Meteorology and National Computational Infrastructure, have been demonstrating the capability of doing continental scale runs at, say, 400 meters using the Australian climate model. And this is an example of that. If you're interested in computation, this used 32,000 processors. It took 5 hours per simulated day and created about 100 terabytes per simulated day. And this is kind of where we got to. And I thought I'd show you a video of this. This is a simulation. I think this one is at 1 kilometer. But the really important thing is it's capturing the weather interactions. There's a cyclone over Queensland. And if you watch closely, you can see cloud formations flowing over the continent. And these are the formation, the dynamic meteorology and the evolution of fronts and the interaction between fronts and weather systems that translate a warming region into significant weather events that threaten a system that might interest you. Doing that globally is computationally eye-watering. It's phenomenally challenging to imagine global climate models running at a few kilometer resolution, but it is now possible. There are groups in Germany, for instance, that are doing that at the Max Planck Institute for Meteorology. And as part of our attempts to build the capability in Australia to take that stuff forward, there was in the 2016 NCRIS roadmap, a proposal developed to provide the technical, not the scientific, but the technical infrastructure to allow the Australian Community Climate System Simulator, the Australian climate model, to be transformed computationally by rebuilding the software by software engineers. And the good news is that was funded by the federal government, and it's just currently ramping up. So what the Access National Research Infrastructure is all about is software engineering, making models easier to use, figuring out how the hell we manage the data, documenting, training, and so forth. And it's a university-led, because it's NCRIS, facility led out of the Australian National University, involving the Bureau and CSIRO and many other groups. And right now, the collaborative agreement is being negotiated. So there are opportunities for other universities to come on board with the Access National Research Infrastructure Initiative to try to build not merely the next generation Australian climate model, but the generation after that. This feeds into many other initiatives, and there's 2 other major initiatives that are of relevance to this community that are now beginning to ramp up. One is the National Australian Climate Service, which is led primarily out of the Bureau and CSIRO. And the second are a series of federal coordination initiatives led by the Department of Agriculture, Water and the Environment, which are looking at trying to coordinate efforts to provide climate information, particularly, I think, by integrated downscaling efforts that should be of relevance to people in the TERN community. So there's quite a lot of money flowing into not merely the technical infrastructure, but the delivery of technical infrastructure to provide services to people who need them. Getting to weather resolving climate models is very expensive. but so are extreme events in Australia. Australian climate extremes cost about 1.8 billion in 2018. And I think since 2018, you'll all be aware of many events since then that have been eye-wateringly expensive. And a question I've often been asked is, would it be worth the investment in knowing far more granular and nuanced information about how climate extremes would change over Australia? There's lots of really interesting questions around that. One of which is in terms of climate mitigation, there's a really interesting question of where you grow the forests to mitigate CO2 in the atmosphere. Because if you grow them in the wrong place, they're likely to get killed by drought and heat waves. And if you don't grow them in those regions where droughts and heat waves aren't going to hit, you miss an opportunity. The same applies to many other questions around mitigation and adaptation. Where should you build dams to mitigate drought risk? And where should you build dams to mitigate flood risk? And how do you design those dams to cope with emerging climate extremes? And then other questions like, will geoengineering simply make stuff worse? Where do we adapt our planning laws to expect new cyclones? There are many questions of this kind that are fundamental to whether or not we can adapt and mitigate to climate change. And without that far more nuanced and granular information coming out of our global climate models, ultimately, our information foundations are too limited. So in order to achieve that, we need much, much better national coordination, and I think that is emerging. We need much more investment, and some of that is emerging, and that will provide us a long road to travel to provide really much more robust advice for impact, adaptation, and mitigation. In the meantime, because you probably don't want to wait that long, the CMIP6 data are now available. They're useful if used carefully. Downscaling products are now emerging, which again are very useful for particular purposes if used carefully, and woven with expert judgment, in my view, informed by the climate modeling. So very much on a case-by-case basis. There's no simple solutions to the use of global climate models in impacts and adaptation research. I think it's important that the detailed, nuanced information in those models is understood before they're too widely used. And I think with that, I was asked to then hand over to Ivan Harrigan, who is next speaker.
Thank you. Can you hear me okay? I've phoned in because my computer updates seem to have wrecked my audio. Can you hear me okay?
Yes. Yes. And I'm stopping sharing now.
Great. Thank you. That was a really awesome introduction, presentation, comprehensive review. I'm going to talk from the other angle, which is the use in health impact assessments. And I'm sharing my first slide now. Can you see that? Hello?
You're all good, Ivan.
Great. So I work for the University of Sydney, and this is a collaboration with the New South Wales Government Department of Planning, Industry and Environment through something called the Health and Human Impacts node of the Adaptation Hub. My background, I actually work for TURN. I am a human ecologist. I'll put my video as well so you can see me. Hi. So I did my undergrad in a degree called human ecology, which led me to epidemiology and health research, environmental epidemiology. And I worked with a group who were studying climate change and health at the ANU. It was a major program, and I learned a lot through that, and got my chance as a postdoc to work with the environmental health team at the University of Sydney, working on such things as this study, which was climate change, heat waves, adaptation measures such as urban heat island and green space intervention. Forwards. Yeah, my computer updates last night seem to have made a step backwards. So I'll try and power through. The heat waves and mortality studies have been done quite a lot and use fairly standard epidemiological methods for studying the history. And so we start with that as the baseline. We get mortality data from the last few years couple of decades. And we get weather data from that same time period, a bit longer, so we can compute things like the 95th percentile from a larger period of time. And then we use that information to define the kind of heat wave, the extreme heat exposures. So that's the second dot point. We use the climatological mean period going back to the 90s. And then we use the mortality seasonality. We have to take account for the fact that there's more deaths in winter than there are in summer to get an adequate representation of the summer heat deaths. And then what we can do is use the statistical relationship between heat and death to estimate the number of, or the fraction of the population who died due to the heat over the period. Now, this is all great, but it leads to the climate change impact assessment method, where we can then estimate estimate the increase in heat-related mortality under climate change and the reduction under the potential implementation of urban heat island reduction schemes, such as greening urban centres. So here's an epidemiological table, which comes from literature that was studying three of the big cities in Australia, Sydney, Melbourne and Brisbane. We chose to use the Sydney, what's called the relative risk estimate, and this can be applied directly to Sydney because this is the study region that we're going to look at. They did a bunch of sensitivity tests on heat waves defined during 1, 2, 3 and 4 days and different levels, 95th, 98th, 99th percentile anomalies, and also adjust for the importance of age. So there's a different one for people over the age of 75 than what there is under 75, and estimate of the uncertainty in the confidence interval. That information gets merged with the observed heat exposure. So this is the historical duration of heat waves, and you can see that Sydney's an enviably much less exposed region than the rest of New South Wales. And this shows you how we kind of disaggregate the population of Sydney into these smaller subregions. Now, across those subregions, we use the observed weather from the past. And so here is a particular heat wave from 2011. And you can see that with the 3-day moving average as the black line, we smooth out a bit of the spikiness, happens day to day. Then we get the 95th percentile. And the bottom graph is actually the number of deaths each day. And the little red bar is that statistical estimate, which is the attributable number or attributable fraction, which is statistically what you would expect occurred due to the increased exposure level of the heat. So we use this method across the population. It has to be applied over large periods of time and preferably over large populations to work. It's not built on individual risk factors. Epidemiology is by its nature a population statistical approach. And so this is the whole Western Sydney aggregate region over the time. The exposures are population weighted, so we do try and get a representative temperature for the people. And you can see winters are always worse, but in summer we get these little red clusters of heatwave related deaths. By age, that's the number just that was attributable to the heat for the historical period. Now, in a climate change health impact assessment, we then use the projections, make a lot of assumptions about, in this case, we assumed that there was no other population changes. It's purely a counterfactual hypothetical experiment about if climate change happened to this current population with these heat health indicators, what would be the future? And then we go further and say, well, if that was the case under a reduced urban heat island effect, would that make a big difference? How to get there is a vegetation cover story, which is about greenness. So the urban heat island measure comes from the New South Wales DPI department and satellite data. And so these are anomalies. The further red, the more that area is hit by more heat, extreme heat. So on heatwave days, that little area adds appreciably to the heat that could have been reduced. This plot shows that when we remove that UHI temperature effect, we can get a different estimated hypothetical temperature exposure. We subtract that from the temperature that was experienced in the historical and then in the projected future. Get to the projections of the future because that's really the crux of today's talks. But here's our estimates with the heat waves estimated over the historical period with no urban heat island effect. We could be reducing this number of heat wave days and getting rid of them. The heat of the city would not be above that 95th percentile that was experienced. And then we would have reduction in the attributable number of heat deaths. In the future, that becomes quite appreciable. So without this UHI additional heat, given the temperature increases, we would be avoiding fairly large numbers of heat wave days and correspondingly more and more heat deaths. I apologise for all the small numbers, but here's a graph. We use the 1.5 NARCLIN models, which are developed with UNSW and the BPI team, and an ensemble average of these as well. With a lot of team discussion about what these mean. There's 3 GCMs, all forced by the RCP 8.5, which is a kind of a higher end emission pathway. I think it's sort of as the baseline, the business as usual case. But then downscaled using different regional climate models. So for each of the 3, we got 3 regional climate models as well. We only choose to use one of them here. So you can see R1 and R2 for each of the access 1, access 1.3. This, I hope, reinforces Andy's comment about the importance of thinking through what projection models you're using. And here's a diagram of how we then just kind of push that population out into the future and say, well, if that temperature was experienced in that counterfactual population, how many heat deaths would we get? With the actual temperature, we've got quite a lot of extra heat deaths. That's a rate per 100,000. And this is a preliminary result. Please don't tweet it. But it's really exciting because the UHI Urban Heat Island Removal Project could reduce it down to that red line, which is going to be pretty important in that 2075, 2100 time period. But that's the total reduction of the UHI. It's actually not going to be that easy. This is the relationship between urban heat island and the percent tree cover. You can see increasing percent tree cover up to 90% is associated with a pretty big reduction in the UHI anomaly, but not 100%. So we're going to have to try hard to get that down. And we've highlighted some policy about how to do that here. I'm going to finish off hopefully reinforcing some of the points that Andy made really well, and in my experience, I was very lucky to work on the Garneau Climate Change Review back in 2008, but it was a period of quite stress-inducing anxiety about how all this data was being thrown at me from the climate science team. And I worked with CSIRO in this rural mental health impact projections to turn the climate data into what's here, the change in grazing yield for agricultural zones, which we thought would make people more vulnerable to mental health problems. And under the dry scenario, there was these big reductions in yield. And in the wet scenario, there was these fairly substantial increases in yield. And so averaging these kinds of things becomes really problematic. And choosing how you're going to do comparisons, crucial. And to finish off with some current work that I'm involved with is turning that into a drought indicator. So the top is the historical durations of drought in New South Wales. And then we've got 3 rows of different GCMs and 2 columns of different forcing scenarios from different emissions pathways. RCP 4.5 would be a nice one to get down to. But it also depends on the wetness or the dryness of the underlying GCM about how that turns out. In fact, the 8.5 seems to have shorter, more intense droughts. So with that, I'll finish off and hand to next presenter, Professor Rickards, and give a really big thankful acknowledgement to all of the collaborators who I work with on that project. Thank you. Over to you, Lauren.
Great. Thank you, Ivan, and hi, everyone. Apologies for not being here for the start. I've got a few things going on at the moment. So it's a great pleasure to be here, especially being back. I've had the pleasure of being involved in turn as the Deputy Chair of the Advisory Board a few years ago now, and have always remained very, very interested in what it is doing. So I will do that awkward thing of sharing my screen. So if I could just get a yay or nay on whether that's working. It's failed to start.
Not yet, Lauren.
Okay, let's try again. So I want to build on the topic of climate change and research, but look at the connection between them in a slightly different way, which is to say,
it's on now.
Terrific, thank you. Which is to look kind of through the telescope from the other end, if you like, which is to say, looking at the impacts of climate change on research itself. And it goes without saying that unless we actually address the impacts of climate change on research, then our research on climate change, not to mention all other research, will be severely hampered. So just this is a really new area of research for me. It's one that keeps me awake at night. Very obsessed with it, but it is still just very much in the beginning phases. So I really look forward to some conversation at the end. So looking at this, as I said, climate change, as we've seen today, and as many of us know in our own work, climate change is increasingly popular as a research topic. And in a sense, we can think of climate change itself. One of its impacts, if you like, broadly speaking, is to stimulate more and more research and research activities around it, particularly in the physical sciences, as you can see there from that 2016 graph. But also, I think it's starting to dawn on many of us that climate change is also a risk, an impact upon research itself. Now, I want to start at the say at the outset here that I realise that there's some fine-grained analyses that go into attribution, but for the sake of argument today, I'm going to be talking about climatic extremes and weather events as if they all have a climate change fingerprint. We can get Andy to talk through whether or not that's a justifiable assumption. But the fact for adaptation is that we have to adapt to everything that's happening from here on in. And so we don't just adapt to a percentage of that, we adapt to all events and to all of the climate as it's emerging. So I want to look at this, and it's building on work that I did with Professor James Watson at UQ, some of you who might know, which was stimulated by the 2019-2020 fires, which for many of us was a very sharp wake-up call, but also starts to look at some of the other ways in which climate change, climatic extremes have been impacting research institutions and practices. So I want to focus on this question of the climatic impacts, noting that, of course, there are many, many indirect climate change impacts as well, not to mention flow-on effects. But this is just at the start, just to sort of start getting our thinking going in these lines. So I want to draw out a few elements of this. Climate and climate change impacts on and affects and influences, creates opportunities for research in all sorts of different ways. I want to look at this question of the field, researchers themselves, of course, because of the context here, research infrastructure, and then just point to some of the many, many other ways in which this needs to be considered as well. So focusing first on the two of them, I'm going to talk through a couple of case studies that look at the two of these things together. So the first one is the work I did with Birchip Cropping Group when I had the honour of being their thinker in residence. And a piece of work that went on and on as the drought itself went on and on. Started off 2006 thinking it was going to be a year or two, and it kept going on and on. And what also happened in that extraordinary drought was that, as many of you would know, particularly those of you in Queensland, New South Wales, it ended very dramatically. So that piece of work became not just a drought study, but it became a climate variability, climate change, climate extreme study. And what it was doing was looking at farm families' experiences of these stresses and the compounding and cascading effects of those. And one of the aspects of it was to train up local women to be some of the interviewers. And of course, they were not immune from this. They were part of this. And in fact, I had to jump into action when one of our interviewers was flooded out in Charlton and was unable to do the record the planned interviews with farm families about the effects of drought, which, as I said, had to become drought and flood. So what that illustrated was that as the that the field, if you like, the world of research that we were attempting to understand was being affected in various ways. So that was being disrupted, if you like. It was also being depleted, and that was the slow erosion effect of the drought, not just in a physical sense, but in an emotional sense, in a social sense. And what we talk about in a piece of work we're doing on this around the dissolution, the lost surety of purpose. And so we're looking at it, we're having to alter our research topic. As I said, it had to broaden out to accommodate the ways in which climate was actually emerging within that particular situation. But it had effects on us as researchers. As I mentioned, one of the interviewers was flooded out. It affected me greatly at the time, had to drive around with a small child in tow doing the interviews at the last minute. And it created huge stresses for research budgets and things like that. There's just an illustration of the sorts of adjustments that many of us have had to make to research budgets as things fail to go to plan. So the second case study here is not climate change research. It's not climate research. It was a study done by colleagues of mine, Blanche Verley and Simone Blom. Blanche is at University of Sydney, some of you might be at. And it's looking at school classrooms and teachers' experiences there and asking a range of questions in the education field. But climate change, climate extremes, climate weather elements of it emerge within that research to become quite dominant. First of all, again, within actually what they were looking at themselves. So in the interviews they were doing, first of all, they were disrupted. It was hard to get and do the interviews. It was difficult not to be affected by the smoke at the time. So sorry, I failed to mention this is during the early 2020, so during the bushfires. Teachers were tired, they didn't have time. And of course, it was about the ways in which the classroom itself was actually part of this broader world, so it really stretched the research topic. At the same time, of course, it affected the researchers as well. And as I said, Blanche is at University of Sydney, just an example of how it was affected. And again, the same sorts of processes affecting the researchers. And so the disruption, the depletion, I'm sure many of us remember that terrible sense of giddiness that you get from breathing too much of the smoke, and that dissolution of where's the field, where's my research, am I in it, am I out of it? And really starting to kind of muddy those waters, if you like. So that's just a sort of short little illustrations of the way in which both the field and the researcher and the relationship between the two is starting to be affected by some of these extremes. Moving on to very much a turn topic of research infrastructure. As I showed Sydney campus there, universities are being affected in their campuses. And this is not happening just in Australia. So here are a few illustrations, particularly to do with sea level rise, looking over in the US, where you've got a whole range of classrooms and laboratories set up in order to study sea level rise, and amongst a whole lot of other marine questions. And at the same time, they are being affected by it. And in fact, some of them are having to do managed retreat. So that is actually closed down and moved to higher ground. Up in the Arctic, we've got similar issues. So I'm sure you're familiar with these sorts of stories where the the research equipment itself is starting to be affected, and therefore starting to affect those vital data flows, which we all know need to be continuous in order to keep those data records coming, in order to inform the climate models that we need, etc. And so, part of the problem here is, how do we start to actually measure these increasingly large disruptions when those disruptions actually put at risk the research infrastructure and, of course, researchers themselves. And here, yes, I am home, darling. Here's one that might be familiar to many of you. So a rather rapid hailstorm, but as we know, hailstorms can be extremely damaging, and this one was no exception. And one of the sort of ironies of this one was that the glass houses that were affected were in fact core to the climate change research, the crop research that was being done there at the time. And I'd be very interested to talk to anyone who was part of that and has been affected by that. And of course, Turns infrastructure is not immune either. And in Tumbarumba, one of the flux towers, and that whole site with all of the many different pieces of equipment was badly affected. And while the tower itself survived, a large amount of monitoring infrastructure was lost. This is again, so you can see there the time, December 2019, and incredibly damaging. Now, in a sense, and I'll talk about this in a second, but there's kind of an advantage for ecological research that is able to encompass fire within its research topic. But that's not always possible. It's not always possible because of the timelines. Think here of PhD students who have a very set time frame, short time frame for some of their projects, and so are not able to necessarily study that slow succession that may or may not occur in those sites after fires. And likewise for projects such as the others I've pointed to that don't always have climate change or climate or weather as part of their research area. So really, lots of implications here to tease out. So just to point to some of the many other aspects of this. So here's an event. Again, the irony, it was actually on Coastal Futures, cancelled because of extreme weather event. This starts to point to some of the many cascading impacts that we need to take account of here, including the reliance of research on shared public infrastructure, particularly electricity and roads. We could put in there airports too, though of course one of the implications of climate change is there's now well overdue questioning of our academic mobility patterns. And so it just points to some of the ways in which climate change is directly and indirectly starting to affect our research practices. And what does that mean longer term for our networks, for our associations, our ways of working, careers, and even the way we think, the way we do research. So what are some of the implications of this? Well, just starting to tease this out, but I do a lot of work helping organisations of all sorts, institutions of all sorts, adapt to climate change. And I've never yet been asked to do one for an academic institution or a research institution. So we've got a long way to go. We've got a long way to catch up. And that's particularly the case because the damage is already starting to affect research. And if you like, it's kind of like being blinded. We know research is so important for seeing into the world, including into the future. So what's it going to mean if we start to become full blind, full silent because of the impacts on research? There'll be a huge irony if we were the adaptation laggards. So we need to get going. There's different paradigms of adaptation. Climate risk management is one. It's an essential one, particularly when you think about all the different hazards and focusing on that future. And looking at anticipatory adaptation, especially for high value assets such as shared research infrastructure, such as TURN. We also have different approaches, vulnerability reduction, so redressing non-climatic stresses. So you could put a big vote in for some research funding injections here, and improving resilience, becoming more agile, if we like. And we know that term is abused terribly in our neoliberal world, but nevertheless, there are some rigidities in academic ways of working, timeframes, for example, that certainly could become a lot more resilient. So I'll leave it there. Thank you so much. Sorry for the background chaos. And happy to have a discussion now. Thanks.
Thanks very much, Lauren. And I know that there are some questions coming in, but I'll sneak one in quickly for you, and then I'll ask some of the other speakers. So you mentioned helping institutions, or the need to help institutions. Obviously, the climate change is going to have really far-reaching impacts that research institutions haven't even thought about yet. But it's such it needs an intense amount of knowledge to understand, as Andy has pointed out, the power of climate models and how people take it into account. How can you picture research institutions such as universities and CSIRO setting up risk management committees around climate and knowing that they're relying on the right information when it's such a fast-moving area of research? Maybe Andy can pop into this one as well.
Yeah, absolutely. Well, I mean, in a sense, research institutions, universities are very similar to many other institutions and organisations. And, one of the kind of main kind of gates through which adaptation is flowing into those organisations is through the existing risk management sorts of frameworks. So building climate risk into that over different sorts of timeframes. And so that can be a productive starting point. And certainly, universities are very alert to risk. But then there's also a range of other opportunities. And I think there's kind of particular ones because of all sorts of unique aspects. I'm thinking here particularly of universities. So for example, you've got the sustainability sort of campus-based activities. They are increasingly looking at climate change mitigation. There's fantastic action on that, but that can expand out in the US. We're seeing it expand out into adaptation and resilience. And there's also, the kind of obvious point that universities are full of researchers. Many of us have a lot of knowledge to share on this. And there's a whole lot of action research that could be done because a lot of it is about simply becoming more attentive to the way weather, climate and other indirect elements related to climate change are affecting us. And so there's a whole lot of sort of experimental work in a social experiment sense that we could really start doing. But I'm sure Andy's got some insights too. Yeah,
I'm sure he has. Andy, you've got some comments here, and Lauren made some fairly provocative comments related to climate models and weather and extreme events.
I mean, at the level of the scales of adaptation that Lauren is talking, I don't know that climate models necessarily fit in. And I think that's perfectly fine. I think a lot of what she talked about and also what Ivan talked about were using multiple lines of evidence sourced from appropriate data streams that helped guide strategies that people want to consider. Global climate models, they give you sort of the broad scale surface, but when you're talking about details around adaptation, there are many steps between what a climate model gives you and the information you need for adaptation and mitigation. So you can think of climate models as one of the lines of evidence that might inform decision making, but I think you need much more sophisticated methods to make sure that you're aware of what you're adapting to. The converse to that, to contradict what I just said, is the climate models clearly tell us about areas of transition risk and physical climate risk. And as many of you know, there's currently a campaign to encourage uni super to divest of fossil fuels. There's an area where universities can act to influence the flows of capital in a way that will help over time mitigate climate change. So there are clearly areas where research feeds into this, but I wouldn't be trying to sell climate model projections to Lauren and Ivan as the basis for how they would build their research strategies.
That's really interesting. And Ivan, obviously, you're working on health aspects of climate change, but just as we've been talking about, it's so complex. And you obviously have to take into account so many different things in making decisions about what you're going to include in your research and so on. Is it the end of an individual researcher? Are we going to have teams made up of lots of really disciplinary experts, etc., to join you in your health research? How are you going to go about incorporating climate science into your health research? What's the pattern? Oh, and sorry, before I finish, and taking into account Lauren's talk on impacts on researchers and picking up on something that Douglas Robertson's put into the chat about maybe a way of mitigating impacts on research would be to have higher degree students working over an extended period of time on a problem with them all rolling through and doing the same issue. Perhaps you can comment on all of that rolled into one.
So I'm the one with the audio problems. Can you hear me?
Yeah.
Yeah, great. I really like that phrase that you've come up with, is at the end of the individual researcher. I hadn't thought of that before. The independent researcher on their own. But I have thought a lot about potentially the end of inter or multidisciplinary teams and the rise of transdisciplinary activities. And so I hope I get this right, but a multidisciplinary team is a bunch of disciplinary experts working together, but they've got their role. Interdisciplinarity is where they come together a bit closer because you're mixing up disciplines with new ways. And then the ultimate transdisciplinary activity is this melding and new fundamental way of seeing the world. And I guess that's where I think it's heading. And that's really hard. I don't think I've ever seen it in action, but I've tried to understand as much climate science as I possibly can. I think I had a head start from my undergraduate in environmental science, and some of the health researchers and demographers, anthropologists that I work with are a little bit limited to start with in learning that stuff. But I don't pretend to be able to do it by myself. So I really need to draw in those climate science experts as much as I can, which is difficult as well because they live in a naturally interdisciplinary world as well and struggle to figure out what I'm saying.
Thanks, Ivan. In the Q&A, Andy, there's a question very specifically for you from Peter Isaacs. I'm not sure I know what all the acronyms mean, but he says, many thanks and fascinating as always, Andy, from its wide range of ecological observations. What can TURN contribute to global climate modelling evaluation, LSM parameterisation and validation, and anything else that helps improve climate predictions and the impact of these on Australian ecosystems?
Thank you, Peter. How long have I got? So observations are critical to how we build our models. And there are very few robust, spatially distributed and consistent observations of terrestrial processes over Australia that are relevant to the timescales that we're particularly interested in. It's extraordinarily hard to get spatially distributed measurements of soil moisture. We can sometimes get groundwater from satellites like GRACE. The thing that fits smack in the middle of the nexus between modeling, land surface model development, and TURN are the observations you provide. Whether it's OzFlux, which is data that we routinely use, those data have been, in fact, we wrote a paper on how fundamentally important the OzFlux data were to the evaluation of land surface models, because it's obvious when you think about it, Australia gets really hot. And it turns out that Australia is about the only place on the planet where there are flux measurements being taken where it's really hot, because most of the rest of the world that's really hot, people aren't living there. So Australia, if you like, provides the data sets that let us understand how to parameterize processes under extreme heat that will flow into other parts of the world as they get hotter. So those data are profoundly important. The other data sets that TERN is involved in, everything from soil carbon measurements all the way ultimately through to almost any data sets that are collected at the land surface, help us parameterize stuff for our global models. The one thing I would say is we don't necessarily need, we like long, continuous, consistent measurements that are over decades, but sometimes that's completely infeasible. Detailed process sets of detailed process observations that might only occur over a 2-week period, where you go from a relatively cool period to a heat wave, or over months where you go from a relatively wet landscape through into drought. Those observations can be worth their weight in gold. So yes, we do like long-term, consistent, high quality controlled observations, but we can actually use other data sets that TERN is instrumental in collecting. And to say those data are profoundly important undersells how important they are. But you do need to have someone like Peter Isaac, since he's asking me difficult questions, I'll throw one back. You need people like him to pull the data sets into very high quality and consistent for the climate modelers and the land surface modelers to use. In the same way as most people who take observations don't get into the computer code, we don't want to get our hands dirty with the observations. We want to use the observations, but the better they're quality controlled and the better they're served, the more we use them.
Yeah, that's really good. So I don't think we've got any more questions coming in. We've had some really great comments from Helen Clue added into the chat if everyone wants to have a look at that about other things that are happening. Oh, we do have another question, and I'll give this one to the panel. What's the most important for TERN on this agenda for the INCRIS roadmap? That might be one for you, Andy.
I don't know what the most important thing is, but I do know the INCRIS roadmap is being swamped by input. If I was to offer one critical piece of advice, is make sure the input you offer to the roadmap is crystal clear, short, and actionable. Not 5 pages of concepts that you think is really important. It has to. I was on the last INCRIS roadmap. We were swamped with information, and the stuff that we could use was the stuff that told us how to resolve the problem via research infrastructure.
And I think that's such a perfect point to end on. So thank you very much, Andy and Ivan and Lauren, for joining us today. And thank you for all of our people who've been a wonderful audience and staying with us throughout the talk. And as I wrap up, I just want to draw your attention to the fact that these are bi-monthly webinars, and our next one is going to be on using high-tech monitoring to look at water in our ecosystem, something which I think is incredibly important, and perhaps I'm going to put on the agenda of the roadmap. Using my chair's privilege to say that. So thank you everyone for joining us, and we will see you again in 2 months. Thank you.
Thank you.
Thanks everyone.